Alright, welcome everyone. Oh, that's this is really fancy, by the way. So welcome, this is the UQCS event. Tonight we have a collaboration event with UQ Racing, which is another society here at the UQ, which is where you'll study hopefully. Or not, you're allowed to come to it. Anyway, UQ Racing are a club here that build vehicles and then they race them. I'm not going to just talk about it too much because they're going to talk about themselves quite a lot tonight. But we're very grateful to have them here. If you've ever been interested in this sort of thing, which we're here to talk about shooting off, UQ Racing do a lot of great work and work that they do has won the prizes, and they have a lot of interesting opportunities. It's not just something that for engineers, and that's why they're here as well. So they want people from computer science and people with like computer science and mathematics backgrounds to come help them because they're in the process of currently developing an autonomous vehicle. Autonomous vehicles need more skills than just wiring things together. Not saying you guys can't code, but you know. Anyway, that's what UQ Racing is here for tonight. That's the talk we have. Just before I pass over to them as well, we promised food for every event. It normally eats pizza, but tonight we're doing something different. So afterwards, we plan to head to the Red Room, which is the local, it's a campus bar. We won't be sponsoring drinks tonight. Also, if you don't know where that is, that's okay, because we'll be leading people over at the end. But we are instead shouting burgers for everyone tonight at the Red Room. So if you want like a burger, you can follow the QR code here or type in that link, and there you can just put in your order, and right at the end of this event, we'll pop over, put the order in. By the time we get over there, hopefully the burgers will be ready. Everyone's entitled to one free burger. You cannot sign up twice, we will be joking. So I'll just leave this up for like 30 seconds to make sure people actually do get this. And then, as soon as that's done, put the guys get burgers. Get straight into the talk. Who's talking about that? Yeah. Alright, so I'll now pass over to UQ Racing. See you guys at the end. Thank you for coming. Please give them a round of applause.
Yes, there will be.
Linda, what'd you do with Firefox? Alright, give us 2 seconds, apologies.
Let me UTS have that technical difficulties.
You just go Google Drive.
Can you walk into it?
Yeah.
Someone's.
That's right.
Yeah. I'm not looking at. Wait a second. Oh, it's yours.
There we go.
Log in on your account.
Alright, there we go.
Awesome. So thank you for coming. Tonight we're going to be talking about our autonomous race car. So, camera's here. Right. So titled it, well, I reckon has a mind of its own. So we're going through the story about autonomous vehicle development. We'll talk about the initial ideas, how we first came to that idea, our software development, and then at the end, what we do in the future and what you can get out of being part of UQ Racing. So tonight, my name's James. I'm your autonomous vehicle technical director at UQ Racing. We also have Matt, our software lead. We have Riley, our software engineer in Perception. We have Caleb, our software engineer in hardware integration. Now, before I begin to get into the technical details, you're probably wondering what UQ Racing is. So, as you can see in these pictures here, we build race cars, and that's the main thing we do. We're a student riding club that started back in 2001, and everything you'll see on these slides here and tonight is all built by us, which is really cool. Our main objective is to compete at the Formula Student Competition down in December each year, where we compete there against all other teams from Australia and New Zealand, all the university student-run teams, to battle it out. So we have been running our electric vehicle for the past few years. In the top right-hand corner, you can see our 2021 electric vehicle Barnacle, which we competed at the Queensland Student Shootout. We came first in most events there. It was a really good learning opportunity and something that we're really proud of. Also at the far left hand there was the most recent competition down in Winton without internal combustion engine and electric vehicle there, and we came second in both events, which was really cool to see. So the main reason why I'm here is that I see that we retired in 2019 and we looked to branch out to other different areas, and FSA introduced the autonomous vehicle category then, which is something that we've been developing ever since. So a bit more about the competition. So there's 7 key events that you need to be aware of, 4 dynamic events. So we have acceleration, where you drive the car for 75 meters and get as fast as you possibly can. Skid pan, where you drive in a figure 8 there. And then we have our 2 long-range events where we drive an unseen track. We have autocross and endurance, which are sort of along respectively. Then we have 3 static events there. We have our design event, which is where we justify our design choices for the car. We have our cost event, where we have to go through justifying the cost choices we've made. And our business presentation, where we're given a case to present to a panel of judges there. What you'll probably note here, which I'll just point out, is that on all the dynamic events, there are blue and yellow cones. Those play into the autonomous part here, which we'll talk more on later in the perception section of this presentation. So that bit about the competition here, and now I'll start telling the story of our autonomous vehicles so far. So in 2020, we retired our internal combustion engine vehicle. It's not left as one electric vehicle. We want to do something different. We wanted to venture out, do something other than what we've seen before. So this sort of starts to develop our journey. As you can see here, we've got buying our first set of cones, we've got LiDAR testing, we have sponsor relations, we've got chassis loading, all that really cool stuff, which we've been working on. I'm going to talk a bit about tonight. So a few team is really keen to get going on this. That's because in Germany, sort of where the competition is set really high, and they've been doing this autonomous stuff for quite some time. Really wanted some of that. Really cool project there, and has lots of code applications. So we had this really cool idea. But what we had to do is figure out how do we start? Where do we go from here? We want to make an autonomous car, but you can't buy one per se. And we make things, that's what our club's about. So I'll talk about the origins of the car now. So we took our 2019 electric vehicle called Chicken, came second at the competition there. Really good solid foundation that we started off there. Had that EV right, except that's meant to be driven by a person. We don't want that, that's boring. Make it driven by itself. So the first challenge really is how do we detect the tracks? How do we know where the car's going to go? How do we see these cones? Well, there's 2 parts to that. First is a LiDAR. We chose to go with a solid state LiDAR, which Riley will talk on later. Basically, that can sense where the cones are and make a depth map of that 3D space. So using this, we know where the cones are. That's one step now. Now we detect which type of cones there are. As you know, there's 2 types of colours of cones, and it's important to know where those are to know where the car has to go. So for that, as you probably would have thought, we use computer vision. So we chose a RealSense depth camera there, using a combination of computer vision, so we can detect where the yellow cones are and where the blue cones are. Really important. So now I have a way to detect the cones. That's really good. The next step is how do we know how the car's travelling? There's no driver there to be able to sense how fast it's going or if something is going wrong. So we need a way to detect speed and yaw and all that sort of stuff. So to do that, we went and sourced an SVG Ellipse N from a sponsor, which is really good, and we've been using that a bit like thing in your phone, and Matt will talk a bit about that in his section of the presentation, how we use that. So we have a way of detecting the cones and knowing how the car's travelling. Now I have to process that. So there's no way on that car to process this kind of large amounts of data. So to do that, we got a ruggedized PC. This PC here, you could drop it off the top of Hawk and it would be fine. Very sturdy, very durable, perfect for what we need, has all our computing power there. So we've got a way to detect cones and to process that to know where we want to go, so we can implement our advanced sort of algorithms there with part planning, all that sort of stuff. So the next part is how do we get this and make the car do these actions? The car isn't built to be driven by a computer. What modifications do we have to make to do that? So the first part is going to be our steering. So we have our steering actuation. Basically, this takes a really large smart motor, which we can feed values into, and that can turn the wheels accordingly. We then have our steering and braking actuation, just for normal track use. Then we have our emergency brake system, or our EBS. Basically, if this car goes rogue, something happens there, we need a way to stop it instantly. Something that's reliable, and we'll do it in a matter of seconds. So you developed a pneumatic system for that, which we're able to stop by hitting our button outside of the track. So the final part that we thought we'd need is a way to be able to manage all these faults. We have lots of different sensors on this car, making sure everything's in check. We need a way to monitor those sensors, and we need a way to take action if something goes wrong. So for that, we developed our autonomous system fault management module. Basically, that monitors these sensors using a microcontroller and is able to activate and use certain inbuilt hardware logic if something does go wrong. There's also some firmware for that board as well. So at the beginning, we had an idea of what we want, so we then need to go procure those parts. So that's really good. Awesome, we got that, we got the foundations. The next part is the software, so the bigger beast here. And for that, I'll pass on to Matt to talk about the software overview and how we develop that.
Hey guys, so to start off talking about the software, I'll point you to the diagram on the right. This is basically an overview of how the software works on our car. So we start at the top with perception and cone estimation. So basically how that works is we use a LiDAR and a camera, and basically we can then estimate the 3D positions of the cones that we see in front of the car. And that's all fed into an algorithm called SLAM that basically maps and localizes where the vehicle is on the track, and part of that involves using the INS. So now the next thing is the path planning stage, where basically we want to generate the optimal trajectory around the track. And what's interesting here to note is that the definition of optimal vastly depends on what mission you're doing. So for example, if you're doing skid pad, the figure 8 track, you have one definition of optimal, whereas if you're doing endurance, you mainly want to optimize for a trajectory that basically allows the car to travel for the longest amount of time, so essentially minimize energy use. And if you look closely there, you'll see the joystick controller. We can actually control our car with an Xbox 360 controller, which is pretty cool. So then the final stage is the more low-level actuation, which is sort of like hardware interfacing and sending signals to the motor stage of that sort of thing. So in terms of tools, most of the code on the car is currently written in C++, but we also do support Python, and we will be and have developed code in Python. The core component of this whole operation is called the robot operating system, which is actually not really an operating system, it's more like a framework. And what it basically involves is sort of like a framework for robotics mixed with a build system, also mixed with a sort of graph-based inter-process communication framework for organizing our project. Some of the other icons you might recognize on there are the triangle is CMake, which is a C build tool, or C++ as well. The GitHub, of course, for our code collaboration, and the Git storage. Eigen, which is a little owl, it's a maths library for C++. And also, we do make heavy use of the Boost C++ like libraries. So, okay, when we start path planning, the first thing we actually need to know is like where we are on the track, right? So, as James mentioned earlier, we use the SVG Systems Ellipse-N inertial navigation system. So basically what an inertial navigation system is a mix of two things. The first thing is an inertial measurement unit, which is basically what's in your phone to tell you what orientation your phone is facing in and that sort of stuff. And it's combined with a GNSS. The difference between GNSS and GPS is that GNSS uses all satellite constellations. So in addition to GPS, it also uses the European version of GPS, for example, for a more accurate position estimation. So basically, all of that data is then processed on board this chip using an extended Kalman filter, basically into a super accurate heading, velocity, and also position. And it's really good because it interfaces with ROS with like one package, so it's pretty useful. So okay, we have this device, but we need to verify actually how good it is. So what we decided to do was strap it to Riley's car and drive it out late at UQ one night, hence the pictures on the side. And also another thing we did was drive it underneath the Connie Knoll parking lot to see how well it coped with like interference and that sort of thing. And what we actually found was that it was really good. It's accurate to about 0.2 meters. You can see because we drove it around about like 3 times, we estimated it had really good loop closure, which is really useful if you're coming around the end of a track and coming back to the beginning to figure out where you are. So great, we now know where we are, so we can continue on. So, I actually wrote the path plan implementation we use as part of a new member project back in 2021 when I joined the team. It's not completely optimal, but it does definitely improve the lap times compared to a naive approach of just like going down the middle of the track. And to basically explain how the approach works, the algorithm works on the discrete unit of cone pairs, the blue and the yellow cones. And we can do that because they're very densely packed in FSE driverless competition. So essentially what we do is we go through each cone pair, start with sort of a random guess about where we are between the two cones. And what I do is straight up feed that off to a giant optimization algorithm from the NLOpt package, which basically then figures out where it needs to put points on the track to generate the shortest path around the track. And then, so that works great, but it doesn't consider the geometry of the car yet. So what I do is then actually feed that straight off to a 2D physics engine from a game, which seems like maybe not an optimal approach, maybe even not a very smart approach, but it actually works really well, and it's actually the most efficient way to do this sort of thing for this sort of algorithm. And the final thing we do is just smooth it with a cubic spline to make it more drivable from the car. And so of course, there's plenty of room for optimization in this algorithm. So in the future, we're going to rewrite it from scratch to include models from our vehicle dynamics team, which I'm kind of putting off because it involves MATLAB. And also, we're going to be using a rapidly exploring random tree instead of the current approach, because that RRT is more just industry standard, and it's also used in other FSAE teams. And we're also going to support multiple events like SkidPad. This approach probably won't work in SkidPad just because the track geometry is so much different. But we will, now that our simulator called FSSim supports that, we can definitely implement that. And definitely real-world testing. Now that the car is progressing really well, we're going to be testing it in the real world in no time. So the final approach, on the left here you can see the car driving in the simulation. And so that's, interesting corner. So it's using the path planning algorithm, and it's also using also a member contributed path following algorithm. And on the right here, you can actually see the simulator actuating the smart motor in the real world. So once it's on the car, instead of there being a little dog connected to the motor, it'll instead be an actual steering wheel, which will be really handy. And on the next slide, we have why we have a simulator. So you can see this is why we don't always just test things in the real world straight up. It's very useful to have a sort of simulation component. So on to the next slide, I'm going to talk a little bit about the embedded systems we have at this club. So firstly, to define what embedded systems are, they're microcontrollers that are embedded deeply inside the electronics of the car. So particularly inside our accumulator, which is sort of our battery, and also inside the engine and that sort of stuff. And the code in this systems is what's called safety critical. So it means there's no room for failure. We have high reliability is an absolute requirement. But yet we also have really limited resources. So one of our projects called the cell management unit, which makes sure that the temperatures of the cells in the accumulator and also their voltages and stuff only has 16 kilobytes of RAM. So you have to work really efficiently. And also the same with the driverless fault management module that James was talking about earlier. That integrates with a thing called the remote emergency stop, which is basically a big stop button that works remotely. So in case the car goes rogue, like on the previous slide, you hit the stop button and nothing is injured. So that's great. Here's the problem, chip shortage, right? Basically, it's really, really hard to source components. So it actually got to the point where I was writing a Python script to scrape one of our microcontroller provider's website and download all the possible chips and then check them manually to see if they were compatible with our car. Luckily, this is something a GPU buyers might relate to, but finally that was resolved and we actually have all the components we need for the car, so that's good. On the next slide, I'm going to talk something a little interesting thing we discovered developing the car. So developing firmware, and in particular embedded C, is really interesting due to the nature of just its resource constrained and interesting vendor tool chains, let's say, and bare metal, and just a lot of hardware interaction. So we use a real-time operating system called FreeRTOS on one of our on our projects, and it's actually a really good piece of software. The thing is, normally when you're developing a C project, you use glibc as a standard library implementation. We don't have space for that. We use newlib instead, which is an embedded variant of that. And the issue here comes because both FreeRTOS and newlib provide their own memory allocators. FreeRTOS 1 is thread safe and reentrant. The newlib one is not. So you might be able to see where this is going. Basically, FreeRTOS implements preemptive context switching. which is basically you have two threads running at once, and they will switch between each other without one thread knowing when it's going to switch or not. So basically, imagine thread A is calling malloc at some given point in time, and then we context switch to thread B, which also happens to start a malloc. Now your heap is corrupted, and essentially you're screwed. It's not really good. So yeah, basically that's a problem. So not to worry, we can just avoid calling malloc, right? No, wrong. Printf actually is one function that you may not think, but actually does call malloc, at least in the newlib variant. That's because if you ever wanted to print a floating point number, and you notice that, say, you get rounding errors, like 0.3 recurring is a common one that comes up a lot, you need space to print all like the 12 digits of that number. So that's why malloc gets called. And there's also other internal reasons in newlib as to why malloc gets called. So essentially, we arrive at our equation, which you can see here. Basically, yeah, theoretically, worst case scenario, printf could cause silent heap corruption and thus silent failure in the car, and essentially have it blow up. So, of course, we fixed that, but it's something really to note with these sort of things, and with software in general. You have to be really attentive to detail and make sure that everything works correctly. That's about it from me. I'm now going to pass over to Riley, who's going to talk about LiDAR perception on the car.
Cool. So, LiDAR perception. What is LiDAR? Well, it's light-dependent ranging and detection. Not in that quite that order, but makes sense. Basically, it's a laser that actually gets shot out of a sensor and is used to determine a 3D position in space. Super, super nice for all forms of obstacle detection, object classification, and mapping. Essentially allows you to build a 3D map of the world around you. Okay, so why don't we see it more frequently? Why isn't it just like built into your phones? Why isn't it everywhere? Well, LiDAR is incredibly expensive, which makes it kind of inaccessible for a team that is just starting out. Okay, so we know that we need a LiDAR because that's basically how you determine where things are in 3D space around you. But we don't want to shill out thousands upon thousands of dollars for sensors that we don't really know if they're going to work for us. So our solution that we came up with was actually to just run it in simulation. Use ray tracing to mimic the behavior of a sensor and try and define what was the sensor that works for us. So, as you can see, on your left, we have a pretty standard mechanical LiDAR, costing around about $5,000. Sees about 4 cones. Not a lot of cones for your money. But we have a LiDAR that is on your right. That one's a cut, $12,000. Sees more than 4 cones. Works for us. Okay, so we know what we want, but we're still operating in simulation, and simulation is only so good. Luckily, the mechanical and mining faculty of this engineering, well, of this university, has LiDARs. So, what did we do? Well, we went and borrowed one from a faculty advisor. We quite literally taped it to a trolley lift, took it up to Conifer Knoll, and we pushed around a track that we made out of the cones that we previously bought. Now, it all sounds like a bit of fun and games and a bit of dance and a song, but this is actually very useful data, because all of a sudden we've gone from only operating in a simulation to operating in a real-world environment where we can actually validate the algorithms that we've been developing in simulation. So it gave us a really nice data set to actually test and trial out the algorithms that we are developing in our simulated pipeline. But okay, if this is so good and we got one for free, why don't we use this? Well, as you can kind of see there, got a real funky, like, spirally scan pattern. And that's not good. Basically, this sensor operated on a non-repeating scan pattern. Used multiple prisms, called a Rayleigh's prism, to actually make a larger field of view, but the downside being that where it's looking isn't constant. It's constantly looking around. And for slow applications, that's great. It means that you have like a really nice field of view. But for a race car where we're rapidly approaching a corner and our LiDAR is pointing somewhere up to the top right away from the cones, not particularly useful. So we looked to automotive because that's what we were doing. And what we found was that there are sensors that were kind of built for us. That one on your right is a hybrid solid-state LiDAR. Lots of words, basically means it has 128 beams that are used through a MEMS system to actually provide a super high density cloud that we can use. And the best part is, it's static, it doesn't move. The data that we see is the data that we get at all time frames. Super useful. So, how do we get that? Well, we called up a Chinese LiDAR manufacturer, sat down with them, had some talks. They were real interested in trying to get their LiDARs into Australia. We were real interested in getting LiDARs. So, we got one of the first production units for a LiDAR that had not even been announced. It was still scuffed from the fact that they had used it in production testing. They quite literally dropped it and verified that it still worked after being dropped, and then sent it off to Australia to be tested by a bunch of university students. And test it, we did. So, we took it to our favorite data testing and collecting spot, the top of Connor Knoll, and we repeated our experiment. But this time, we upgraded our pushcart. So, instead of pushing a cart around a track, we built a slightly larger track, and we held a LiDAR at the top of a convertible. Again, bit of a silly song and dance, but then we actually took that data and validated our algorithms. All of a sudden, we've progressed from simulation to real world to actually moving at a reasonable pace. And we can see that we can detect cones at a pretty nice range. That is extending out to around about 40-ish meters, which means we've got a view of about 40 meters in front of the car at all times of the cones that we need to navigate around, which is very, very nice compared to mechanical LiDAR solutions like we saw in the first simulation page, which could have told us where cones are promptly 2 meters ahead of us. So, okay, I've spoken a lot about LiDAR, but if LiDAR's so good, why did we have a camera in our system? And why is Elon Musk so adamant that it is the only sensor you need? Well, that's because LiDAR sucks at detecting color. And if you might have noticed, we have yellow and blue cones that tell us what side of the track that we're meant to be on. Okay, let's add a camera. And that we did. In fact, the member that wrote this algorithm didn't actually have access to any of the track data that we had that had our GoPro footage. So we went to our YouTube channel and scraped a 480p video off YouTube to collect data to train his YOLO V5 algorithm on. And boy howdy did that thing find cones. So we actually trained it on 2 data sets after we actually properly inducted him into the team. And that was a data set from a simulation and a data set from actual track days. So yes, we want to operate in real world, but as we saw before, operating a simulation is kind of necessary if we want to validate anything that we're doing without making a $100,000 mistake. So we generalized our algorithm, and we were able to detect cones both in real world, well, in real life and simulation. But okay, if camera is so good, if camera can tell us where cones are and what color they are, why do we even bother with the whole LiDAR situation? Well, that's because cameras kind of suck at telling us where things are. They tell us what color they are and like roughly where they are in the image. But as for 3D space, yeah, they can make a pretty good guess. But if you're trying to operate and trying to do SLAM, then a pretty good guess generally doesn't cut it. So we've got a sensor that's really good at telling us where things are in 3D space, but horrible at telling us what color they are. And a sensor that's really good at telling us what color things are, but sucks at telling us where they are in space. Well, the solution to that is combine them. Why not? That's what we did. So that GIF in the bottom left down there is actually a pinhole model of LiDAR data overlaid onto a 2D image that our camera can actually use to allocate a depth to the pixel in its image. So you can kind of see like 4 little pizza slice looking things in the middle of the image there. And those are the codes. And they protrude into this white immense background that is essentially just points that we don't even care about. So we've gone through a nice little journey of, okay, we want to find cones, we found cones, we want to know how far away they are, we know how far away they are, we want to know what color they are, and we can find out what color they are. And this full intertwined system makes up the small piece of this car's code that is the perception algorithms. This is all just to tell us, yep, there's a cone over there that's 4 meters away, and we're pretty sure it's blue. But this is something that you could also work on if you join the team, and Caleb will take you through that.
Yeah, so this is the part where I beg you to join the team. Look, like we have a lot of fun, and we come across some big challenges and just work through them. We get to play with some cutting edge technology. But I really do recommend you join the team because there's a lot of benefits, all those are just listed, plus we do need the help a little bit. So as James mentioned earlier, we also have a regular car, a regular electric car. And so between the electric car and the autonomous car, our year ends up looking something like this, design, build, compete. So in the first quarter of the year, we all come together and we design our car in its entirety. There's a good chance to learn about all kinds of systems that you might never see in your coursework. From there, we then build our cars, and that takes us all the way up until about November, October. For the electric car, that's literally physically building the car. But for the autonomous one, that's more focused on our, making our code, developing our algorithms, really being flexible with that. We kind of iterate a lot during that with the software side of it. And then the most fun part. In December, we head down to Winton Raceway in Melbourne. We compete against other teams in the autonomous and the electric categories. There's currently 3 other teams doing AV in Australia, so we get to collaborate with them as well during that time. So you learn and design, you bring your designs to life, and you have a heck of a lot of fun at the competition. But on top of this, we have a lot of great industry connections. Our team heavily relies on sponsor support for monetary and design assistance. And most of our sponsors are only looking for one thing, and that's access to graduates. So there's regularly positions available at our sponsors and our alumni's workplaces through the team. And just some of those, I'll just mention some notable ones. We've got Emerson, a Brisbane-based company that do autonomous drones for spatial mapping applications. MES, who do dual fuel conversion kits for mine trucks. And Franna, who create cutting-edge control systems for pick and carry cranes. And those 3 companies all use technology and systems that we get experience with on the team. So that's why they really want us to join them. So we have a QR code here that you can scan. This will still be up during question time. So I recommend you get on that, just a form that you put your name, email, phone number in. So yeah, if you're interested. That's about all we have to present. So that's just a story of where we started, where we've gone, some of the challenges we faced. But we're going to spend the rest of the time doing questions. So anything technical, anything about the team, bring it on. One of us will answer you. Yeah.
Whose Beamer was that you drove to test the camera?
She's not here, but she was the tech director last year. Yeah.
Do you have to make a new car each year? Is it inspired? Yeah, do you have to do it?
So with autonomous, we're still working on the one car, just trying to get that done.
Yeah.
But with EV, we make a new car every year because we can improve it. We can make it better. That's why we make a new car every year.
Yeah. Does it, how much inheritance does it have from the previous year? Do you reuse the chassis? What kind of...
Yeah, absolutely. So I think the best way to answer that is give you an example. Between last year's EV and this year's EV, the only major change we're aiming to do is the drivetrain. So we're trying to keep the chassis and all the other components very similar, but we're changing what motors we're using and how we're powering those motors. That's basically like the only thing we're going for. So it is very iterative from year to year because we try to reuse a lot of our tech.
Okay. Yeah. This is a more serious question this time though, but I noticed that you didn't mention you using any proper pathfinding algorithms for this instead. Why is that the case though?
Say by pathfinding algorithms, do you mean something like A-star?
Yeah, probably like that, yeah.
Yeah, so that's because those sorts of pathfinding algorithms like A-star operate on a graph data structure. So certainly we could, so we operate in a continuous space. So certainly you could like discretize your space into like a grid, but then the problem still remains that you have to factor in the vehicle's geometry, because usually, say when you're doing A-star and navigating an agent around a maze, generally that means that you just consider a point model of the agent, and you certainly can do that for the car as well. But basically, if you did A-star on this sort of track, it would, because in order to get a good path, you would need to have such a high, like a very dense grid. Essentially, it would take a lot of compute compared to just sending it off to an optimization algorithm that's designed to deal with big problems. Essentially.
Well, how powerful is your computer though? I mean, it's not a Raspberry Pi. It's like
Yeah, we do have a pretty powerful computer, but a lot of that time is spent doing computer vision and LiDAR processing. Those are essentially the biggest compute challenges on our car. So we want to allocate the maximum possible compute time to do computer vision. Because even something like YOLO V5, right, which is what we use for detecting our cones, that is like, even though that's more optimal than say like YOLO V3 and stuff, even still, even when it's running on the GPU, it still uses a lot of like compute that we need to allocate it to get even like above 10 FPS or something like that. Does that make sense?
Yeah. Okay.
Yeah, cool. Anything else? Yeah.
You mentioned for your autonomous vehicle that you got a previous car body, basically, and started from that. Why start with a car body that has limitations because it was probably driven by a person previously? Why not do a whole new design and leave out the driver?
So one of the rules of the competition is that the car has to be able to be driven by a person as well. So it's both a human-driven and computer-driven car. So it's just easy to start something that's already halfway there. Yeah.
Do you have any non-student members? Like, I'm graduating soon.
I don't think we do, no. I think it's strictly a student competition.
Oh, Shane, that was a really good question as well, because I'm sort of a similar situation there.
But although like non-current student members don't directly contribute to things, we do have a very large network of our previous members that we seek advice from quite frequently. We'll host design reviews where we sit down in a room with them and just like ask them to pick apart our designs and throw literally everything that they have, all of their knowledge base at it. So even if you're interested in this thing and you have expertise that might be useful, yeah, that's still incredibly good for the team.
Okay.
How do you sort of like learn all these extra things that aren't from uni, like FreeRTOS or this sort of, it's pretty deep embedded C programming that's, advanced at uni. How do you guys go about teaching yourselves that skills and getting new people?
Yeah, for that, I went to a school that had a robotics program at school, and that was all using, so those also run on microcontrollers, so those are embedded, and in particular, I was using the ESP32, which is it's sort of an IoT microcontroller. I would say that's probably the best platform if you want to learn FreeRTOS, because it's a lot simpler to set up. When we're using like NXP, like microcontrollers, for example, those most of them don't come with FreeRTOS by default. With the ESP32, you can just configure it. So that's basically how I learned it. And pretty much all I did was just read the docs. In particular, the docs for FreeRTOS are like exhaustive. They're really, really good resource. And so yeah, pretty much read the docs, read some example code, try compile a few examples. Even if you don't have a microcontroller, you can use QEMU with a Cortex like M4 emulator or something, and then just run it on your computer locally. And definitely, yeah, make heavy use of GDB as well.
Sorry, just on that as well. My experience coming into the team, I didn't know anything about spatial data or any of the hardware stuff we use, the CAN bus, all of that. Didn't know anything about it. And the team taught me everything I need to know. So don't feel like it's a limitation, because we love teaching you guys how to do this stuff. Yeah.
Did you have a question from before?
I suppose on that topic I was going to ask before, what's the lowest level of ability for somebody interested in joining?
We take in first year students that haven't even learned how to program in terms of like actually doing the more software-y side of things. But it's sort of a case of, even if you don't know how to do CAD, which I presume most students at university don't, they come in, they sit down, they have someone who's been doing CAD for the car for quite a while, and they make mistakes. They learn, and they are taught how to do things. It's all about just getting experience with a lot of these things. And that's something that the team does very well, is offer you experience. Yep.
When and how often do you meet?
Yeah, sure. So we have formal meetings once a week. That's our team meeting. There's subsystem meetings as well, which are a little bit more technical focused, and they're sort of like, if you're actively doing design work, go there and you can share thoughts. But otherwise, we mainly just spend our time up in our, design center, aka Croc, which is the second level of Menserg. So although we only have formal team meetings once a week, there's pretty much always someone in there that you can bounce ideas off, talk to, have a good time with. Yep.
What's your powertrain like these days? Do you do like four-wheel drive or hub motors or
Cool.
anything like that?
There you go.
So every other year until now, we've had a single motor in both EV and IC cars. But this year is the year that we're starting to develop hub motors. So we have our motor in the wheel with the gearbox in there as well. We're going two-wheel drive just on the rear this year. And that gives us the opportunity to torque vectoring, which is where you can have varying torque applied to your wheels based on what your system requires for corners and whatnot. So this is our first year that we're doing multiple motors. Good question.
Just have a question here from the chat. Do you get an Altium license with membership?
Yes, I think so.
We have the sponsorship now.
Yes.
Yes.
Can confirm.
Yeah.
Does that mean you can download it on your own computer? You don't have to remote desktop or anything?
Yeah, I can answer.
Yeah.
Yeah, so ours can give out free education licenses
Yeah.
for everyone to use. We also have a sponsorship with them where, camera, right? Yep.
Yeah, we can.
We also have a
They're on
sponsorship with
Zoom.
them where we get 10 sort of unlimited access memberships. So yeah, everyone on the team, as soon as you join it, you get Altium. We've also got all our software as well. So yeah, everyone has access to that.
Okay.
Yep.
Do you do any monitoring and optimization of like the passive chassis dynamics? Like how it handles and how the conditions might change from day to day in your setup?
That is a very good question. As someone who writes code, I am not entirely qualified to answer that.
So was the question, do we model how the dynamics of the vehicle changes based on the day's conditions?
Oh, no, do you log and try to optimize like how it handles physically, like your suspension and
Okay, yeah,
brake
so
levels and things like that?
when we're designing the car during that first quarter of the year, we do optimize everything. We have some specific test cases that we use. We talked about the skid pad competition earlier. So we'll optimize our suspension and steering, just how it feels for the driver based on that event. And that tends to have a trickle-down effect into our other events that gives us a very well-optimized car. And then during that build and compete time, we collect absurd amounts of data to then drive those decisions for the next year.
What does this skid pad mean? Like, to me, it means people doing skids in there, like, cars, and I'm sure it's not quite that.
Well, I mean, you do end up with a lot of people doing skids in the event. So you can see on the second image on the top left with that figure 8,
Yeah.
that's the skid pad track. It's you just have to do 2 circles to the right and then 2 circles to the left and you exit the track. And you just got to do it as fast as you can.
Okay.
Yeah.
Do you do a lot of like CFD, the computational fluid dynamics and stuff? Is that within the scope of this?
So with the EV cars, yes, we do. So all of the aerodynamics is designed by us. We simulate everything before we build it. We target about, I think last year's goals were, or last time we designed a car was 60 kilos at 60 kilometers, was our downforce goals. And I believe we were relatively close. I think we hit about 40 kilos at 60 k's, which is still pretty good.
Okay, how do you measure the downforce?
We have linear potentiometers on our suspension. So we measure suspension travel, and that'll tell us, you can do the math from there, and that'll tell us how much force is being applied to them, because we know the spring rates.
Okay.
Yeah. Just being conscious of time, there's no more questions from anyone? No? Alright, yes?
Sorry, the autocross and endurance, how long is that track?
So the endurance is 22 kilometers. I can't remember how long autocross is,
Is it
unfortunately.
shorter or
It is much shorter, yeah. It's about yeah, it's like a tenth of the distance. Yeah. Excellent. Right, we might wrap it up there then.
Cool, right. Everyone give UQ Racing a round of applause. So if you're interested in learning more about them, I'm sure you can just come along and talk to them afterwards. Are you guys all sticking around? Oh yeah. So they'll be in the red room if you want to come, or even just after this talk, just come down and ask some questions. When do you guys regularly meet up? When can people come and meet you?
Wednesday.
Wednesday?
Wednesday.
Wednesdays?
Yeah, Wednesdays at 6 is our team meetings, or you just come up to Croc and chat to us to Menso Jaw.
Awesome. So, with that, that's the event for tonight. We have a gift for our speakers tonight. So, UQ has mugs. We'll give for all of our speakers, and we have 4 mugs here for you guys. So, thank you for coming and talking, and hope to see you guys around.
Thank you.
We'll be.